In this video, we're going to learn how to calculate probabilities related to normal distributions. In the core part, we have already learned about some basic features of normal distributions. We know that in real life, normal distributions are good approximations for many statistical and probability distributions. And we have learned that normal distributions have basic features like this. Now we're going to explore more mathematics behind normal distributions. Mathematicians found that normal distributions can be described by a function like this. In this representation, if we express the function fx in this way, then it means that the random variable x follows a normal distribution with mean mu and variance sigma squared. In probability theory, we can use n mu sigma squared to denote normal distributions. In this example, when the mean is 1.3 and the standard deviation is 0.8, this normal distribution can be denoted by n 1.3 0.8 squared. Please pay attention that it is not 0.8 here, but 0.8 squared. Because the second parameter in this notation always refers to the variance, but not the standard deviation. Then in this mathematical representation of a normal distribution, the area under the curve refers to the probability when the value of x happens to be in this range. In this case, the probability that x is between minus 0.5 and 2 can be represented by this area under the curve and this definite integral. In this way, we can see that the values of fx are not exactly probabilities. Indeed, this fx means probability over x. So this fx is called the probability density function of x. Unlike the probability functions that we have learned for discrete random variables, we use probability density functions to represent the distributions of continuous random variables. For this probability density function of the normal distribution, if the value of mu changes, then the curve will translate horizontally like this. And if the value of sigma changes, then the curve will vary like this. In other words, when we are given that x follows a normal distribution with mean mu and variance sigma squared, then we know that the corresponding probability density function is equal to this expression for all real values of x. We also know that the expectation of x is equal to mu. And that means we know that this integral is equal to mu. What's more, we know that the variance of x is equal to sigma squared. And that means we know that this integral is equal to sigma squared. Why these formulas are true is beyond the scope of this video. So right now, let's accept them as facts. Besides, it is useful to know that for any continuous random variables, including normal variables, these properties for discrete random variables are still true. Also, for continuous random variables, because a probability is represented by a definite integral like this, we can deduce that the probability that x is equal to k is always equal to 0 for any real number k. This makes sense because it is extremely rare for x to be exactly equal to k if x is continuous. For example, when we know that the temperature is equal to 25 degrees Celsius, that means it may be 25.01 degrees Celsius, 25.001 degrees Celsius, 24.999 degrees Celsius, etc. There are infinitely many possibilities. So it is extremely rare for the temperature to be exactly equal to 25 degrees Celsius. Therefore, theoretically speaking, for truly continuous variables, we can describe that the probability that x is equal to k is equal to 0 for any real number k. Based on this result, we can conclude that these four probabilities are all equal for continuous random variables. In other words, the equal sign of inequalities will not affect the probability in the cases of continuous random variables. Another property of the normal curve that we can obtain here is that the area under the entire curve is equal to 1. This can be understood as a basic property of probabilities that the probability of the entire sample space is equal to 1. Now let's come to the most important part of this video. That is how we can evaluate these normal probabilities. For this definite integral of the normal curve, mathematically there is no closed form solution of this integral. In other words, we cannot make use of simple functions that we have learned to evaluate this probability. However, although this definite integral cannot be evaluated analytically, we can simplify this definite integral by using the substitution z equals x minus mu over sigma. In the core part, we have learned that this quantity z is known as the standard score of x. After this substitution, we can see that now the integrand becomes a lot simpler, like this. And the lower and upper limits are just the standard scores of the original limits. For this probability density function of z, we can see that it is actually the normal curve of which the mean is 0 and the variance is 1. We call this special normal distribution the standard normal distribution. And this random variable z is then called the standard normal variable. That means any normal curves can be transformed into the standard normal curve in this way. Although we still cannot evaluate this definite integral analytically, we can refer to this standard normal table for the areas under the standard normal curve. Here, each value in this table represents the area under the curve from z equals 0 as indicated here. Let's take a look at a few examples and see how we can make use of the standard normal table. To find the probability that z is less than or equal to -2, firstly we need to visualize which part of the curve we should focus on. As the standard normal table can only give us the area under the curve from z equals 0, we need to consider symmetry and difference of areas like this to obtain the required area. For the first area, it is just half of the normal curve, so it is equal to 0.5. For the second area, it can be obtained from the standard normal table. From the table, we need to look for the value when z is equal to 2.00 like this. We can see that this value is 0.4772. Therefore, the required probability is equal to 0.5 minus 0.4772, which is 0.0228. Then, to find the probability that z is greater than or equal to -1.06, again, we firstly need to visualize how the area looks like. Afterwards, by symmetry and sum of areas, we can obtain the required area like this. For the first area, it is just half of the normal curve, so it is equal to 0.5. For the second area, it can be obtained from the standard normal table. From the table, we need to look for the value when z is equal to 1.06 like this. As a result, we know that the result is 0.5 plus 0.3554, which is equal to 0.8554. Next, to find the probability that z is between -1.23 and -0.21, again, we need to visualize where the shaded area is. And then we know that we can obtain this area by considering the difference between these two areas. Both areas can be obtained from the standard normal table. When z is equal to 1.23, the value from the table is 0.3907. When z is equal to 0.21, the value from the table is 0.0832. As a result, the required probability is equal to 0.3075. Lastly, to find the probability that z is less than or equal to -2.51 or z is greater than or equal to 2.51, again we need to identify the required area like this. And then by symmetry, we know that this area is equal to the double of the difference of these two areas. When z is equal to 2.51, the value from the table is 0.4940. So the required probability is equal to 0.012. Finally, let's take a look at how we can handle a non-standard normal variable. In this example, x follows a normal distribution of which the mean is 12 and the variance is 6.25. Now, to find the probability that x is less than or equal to 15, firstly we need to consider z, which means the standard score of x. That means by considering that x less than or equal to 15 is equivalent to z less than or equal to the standard score of 15, we can standardize this normal variable x. And thus we can obtain the required probability by referring to the standard normal table. To calculate the standard score of 15, please pay attention that 6.25 is the variance, but not the standard deviation. So we need to take the square root here. As a result, we know that the probability that x is less than or equal to 15 is equal to the probability that z is less than or equal to 1.2. And then by visualizing the required area and splitting it into two parts, we know that we should look for the value from the table when z is equal to 1.20, like this. Therefore, the required probability is equal to 0.5 plus 0.3849, which is 0.8849. This is how we can calculate probabilities related to normal distributions.